Hemodynamics is the study of all the factors that affect blood flow. If you look down at the bottom, blood flow by definition is the volume of blood that flows through any tissue in a given time period. It's usually given in milliliters per minute. These four are the big four factors that affect this blood flow. One is blood pressure. Higher the pressure, the more blood can flow through a tissue. Vascular resistance is actually the opposition of blood flow. Vascular resistance is due to friction between blood and the blood vessel. And if you increase that resistance, blood flow will actually go down. Venous return is bringing more blood back to the heart. So you can imagine if venous return is down, blood flow is down. And then finally, velocity. Velocity is the speed of blood flow. So we're going to take a look at each of these four factors and how they contribute to blood flow. Let's look at first blood pressure. Blood pressure is produced by your heart. And we know when the heart contracts, that pressure goes up, and I should say the ventricles. When the ventricles contract, the pressure goes up. When the ventricles relax, blood pressure goes down. So this graph represents systemic blood pressure throughout the systemic circuit. So you'll notice here we have this vertical axis is pressure in millimeters mercury. This axis here is throughout the systemic circuit. So you would start really at the left ventricle, then aorta, arteries, arterioles, capillaries, venules, veins, vena cava, and then right here would be the right atrium. So what we're looking at is the pressure differences that occur throughout the systemic circuit. You'll notice that blood pressure is going to go up and down, all right, and that again is based on what that ventricle, that left ventricle, is doing. The left ventricle is in systole. If it's contracted, pressure is high, systolic blood pressure. When that ventricle relaxes, pressure goes down, that's diastolic blood pressure. Notice a couple things. The first is this is going to be the highest right off the bat. And that makes sense. If the left ventricle is producing the pressure, then the aorta must have the highest blood pressure, and it does. Also notice that it doesn't significantly decrease when you go to arteries. It's about the same in arteries as it is in the aorta. And that's why you can take someone's blood pressure in a systemic artery, like the brachial artery of the arm, very commonly used to determine someone's blood pressure. It doesn't start to drop until you get to arterioles and then capillaries. So we've learned this number already. This is that beginning of a capillary is about 35 millimeters mercury. Then at the end of a capillary, it's down to about 16. And then it keeps dropping in venules and veins. And the right atrium can get all the way down to 0. So you'll notice there's a trend here. Blood always goes from high to low pressure. You're not going to be able to move blood somewhere where there's a higher pressure. So wherever you need blood to go next, it better be a lower pressure. Pressure is always going to be lower where that blood is going. Notice that there's a purple line shown on this graph. This purple line represents MAP, mean arterial pressure. Mean arterial pressure is the average pressure throughout a cycle. So this just kind of shows us the average pressure here from when you go from an aorta, arteries, arterioles. Notice it doesn't significantly drop. It does drop a little bit, or you wouldn't be able to move blood. It doesn't significantly drop until you get to those arterioles, then the pressure drops down. And we're going to want to practice calculating MAP. There's a pretty easy equation to calculate MAP if you know the systemic and diastolic, or systolic and diastolic blood pressures. So this graph is going to help us just understand a trend here of blood pressure. Let's look at vascular resistance. Vascular resistance, by definition, is the opposition to blood flow due to friction between blood and the walls of the blood vessels. If vascular resistance goes up, blood pressure is going to rise in order to maintain blood flow. Said another way, if vascular resistance increases, blood flow is going to drop because there's that opposition to blood flow. But to compensate for that, blood pressure goes up. So this is an extremely important thing to understand because a lot of individuals have high blood pressure. And high blood pressure is not all the same. It's not caused by the same thing. So we need to know the different causes of having a high blood pressure. But a lot of it has to do with this information on the slide. When the lumen size, the size of the lumen decreases, that's going to increase vascular resistance because you're constricting down on that blood, and that's going to increase the friction between the blood and the blood vessel. If the diameter of a blood vessel increases, we call that vasodilation, that reduces vascular resistance, which can help reduce blood pressure. So let me say that again. When the size of a blood vessel lumen decreases, we call that vasoconstriction. Vasoconstriction increases resistance, and because of that increased resistance, blood pressure goes up. Okay? There are some things that decrease the size of the lumen due to diet. An individual with a diet that's rich in cholesterol and fatty acids, saturated fatty acids, they develop atherosclerosis. And the buildup of that plaque inside of the arteries reduces the size of the lumen, and that contributes to high blood pressure. Blood viscosity is a thickness of the blood. If an individual overproduces red blood cells, that blood becomes thick, that increases resistance and will increase blood pressure. The opposite can be true with someone with anemia. Remember, anemia is low red blood cells. If you have low red blood cells, your viscosity is low, your resistance is low, and your blood pressure can be low. So a lot of individuals with anemia have a low blood pressure, hypotension, as opposed to hypertension. Total blood vessel length. Total blood vessel length. Let's see. What would affect how many blood vessels you have and their length? Well, one contributing factor to blood vessel length is obesity. When humans put on weight, unhealthy weight, adipose tissue, to supply that adipose tissue with blood, it grows blood vessels. And there's an estimated 400 miles of new blood vessels for every 2.2 pounds of fat someone puts on. So that's 1 kilogram. So this number comes from your book, but if you put on 2.2 pounds of fat, to supply that fat with blood, you extend your blood vessels 400 miles. And these are all these little capillaries in the adipose tissue. I do that over Christmas break. Christmas break, I put on a few pounds. So I grow miles upon miles of new blood vessels over Christmas. And that can impact my blood pressure, because when total blood vessel length goes up, that increases vascular resistance. And that can lead to an increase in blood pressure. So these have a lot to do with why someone might develop hypertension or high blood pressure. Another one that's very important to blood flow is venous return. Venous return is the volume of blood flowing back to the heart through the systemic veins. And this is largely due to this pressure difference between where it's coming from, the venules, and where it needs to go, the right atrium. You want a nice big pressure difference. 16 to 0 is a nice pressure difference. Blood will flow very well if it's under 16 millimeters mercury and it's heading towards 0. That's a nice pressure difference for venous return. Sometimes we have to help this venous return. There are 3 mechanisms that promote venous return. One is this pressure difference, right? Pressure generated by the left ventricle. Because remember, this 16 is really due to that left ventricle. It's just a lot lower because it's farther from the left ventricle. But if your left ventricle is not pumping blood adequately and not producing enough pressure, that's going to mean this number's low. If this number gets low, it's going to be harder to get blood into that right atrium. So individuals with quote-unquote sick hearts, hearts that aren't producing enough pressure, can have improper venous return. Their blood will begin to pool in the veins, and that's not good. Another thing that helps venous return is what's called the skeletal muscle pump. That's what's shown in this figure here. It has to do with veins being nestled in between skeletal muscles, like in your legs. And when those skeletal muscles contract, it squeezes on those veins, these deep veins in the leg. And when you squeeze on these veins, it helps force blood. Well, it's going to help force blood up and down, but luckily, notice what's located here. Valves. So the skeletal muscle pump requires those valves to be present to make sure that blood goes up and not down. So this is why we need to walk around. Don't sit for too long, right? Especially older individuals. If they're going on a long trip, they need to get up and walk around. That helps their circulation by causing skeletal muscle contraction, squeezing on deep veins of the legs, and helping venous return. Again, if individuals sit for long periods of time, blood can pool in the veins. And then finally, there's what's called the respiratory pump. This kind of has to do with pressure changes in your chest. And when you're breathing, the pressure changes within your chest squeeze on veins in your chest and can help force blood back into your right atrium. So this breathing helps to properly bring blood back up. So that's venous return. We want a nice venous return to get blood back up to your right atrium. Velocity. Here's a graph showing us velocity changes throughout our systemic circuit. So you'll notice that this is looking at the same path, aorta all the way back to vena cava. But this graph is showing 2 different lines. One line represents the velocity, all right, that's the black line. This is, where is blood moving the fastest? Where does it happen to slow down? And the green line tells us why. The green line represents what's called cross-sectional area. Cross-sectional area determines velocity. In fact, velocity is inversely related to cross-sectional area. What that means is when you have a low cross-sectional area, velocity is at its highest. So this one gets a little confusing because you're looking at the capillaries and you're saying, whoa, why do capillaries have the greatest cross-sectional area? I thought they were the smallest. But what we're doing is we're looking at all of the capillaries together. So if you add up the cross-sectional area of all capillaries, that is much, much greater than a single aorta. There's only one aorta. It has a certain cross-sectional area. But when that blood starts to branch into more arteries, the overall cross-sectional area goes up a little bit. And because that blood is going into a larger area, it slows down a little bit. Then those arteries branch and branch and branch into many, many, many little arterioles, but collectively all those arterioles have a greater cross-sectional area, so blood slows down again. Then when that blood goes into all those capillaries, because those arterioles keep branching and branching and branching, all those capillaries have a huge cross-sectional area. And that causes blood to slow right down in your capillaries. Then capillaries merge together to form venules, but there's less venules than capillaries, and there's less cross-sectional area, so blood actually starts to speed up a little bit in your venules, veins, and vena cava. So this is the velocity inversely related to cross-sectional area. It's the fastest in your arteries. It slows right down in your capillaries, and this is very useful because it gives us time to do all that exchange, all that capillary exchange. But the key difference between this and, say, blood pressure, where blood pressure always drops, is velocity goes up a little bit. Velocity increases as it returns to the heart. Not to the speed as it is in the aorta and arteries, but blood moves faster in veins than it does in capillaries. So that's the trend to focus on. This high velocity in your arteries, low velocity in your capillaries, but it starts to speed back up in your veins. And that has to do with the fact that that cross-sectional area goes down again. Next video, we're going to review some of this stuff because we typically need a lot of review when it comes to understanding all these different factors that affect blood flow.